Okay, batteries cut out. So I'm going to go through this little chart that I made, and I didn't realize my battery's off, but I went through the first one. I'll just go through these last real quick. This is comparing forces in each chart. These are all hydrocarbons, and I have methane, and then propane, and then pentane, and then decane, and it's getting progressively higher. Hydrocarbons are always LDF force. If they're light and they have few electrons, they're low magnitude. As the molar mass goes up, the number of electrons goes up, the polarizability goes up, so the magnitude of force goes up. And then this just shows you how your properties are related. A low force will always give you a high vapor pressure, and a high force of attraction will give you a low vapor pressure. Well, for every other force, a high vapor pressure results in a low boiling point, and all your other properties are low. Low vapor pressure gives you a high boiling point, and all your other properties are high. The only other property that I think I was thinking of before that I didn't mention would be volatility. And volatility would go right along with vapor pressure. If you have a high vapor pressure, you're going to have a high volatility. That's the ability to become a gas. If you have a high force of attraction, you'll have a low volatility, a low opportunity to be gas. Okay. The next bracket would compare methane to um, carbon tetrachloride, and then I have a bromine substitute and an OH. With all four things being the same, this would be LDF, this would be LDF. Putting on one bromine would have a difference in electronegativity that would give it a dipole, and then the OH would give you a hydrogen bond. So the hydrogen bond would be the highest, the lightest, low LDF would be the lowest force. So high vapor pressure, high volatility, low vapor pressure, low volatility. And then your forces, with a high volatility, everything's low. With a low vapor pressure, everything's high. In the back, okay. This is a good look. These are all acids, and then it's hydrogen. And then this chart, I can mention it. What we're looking at is your difference in electronegativities. Okay, so if I had like H2, and I think hydrogen's 2.1 minus 2.1, so that would be 0 difference in electronegativities. So that would be strictly nonpolar and 0 in ionic character. As your difference in electronegativity goes up, that would increase your polarity. And when you get past 50%, then you can really see it's kind of what we see as a gray area. That's when you go from being extremely polar covalent to ionic, and that's the condition that acids get in. So I think chlorine's 2.5, 3.5. So if I looked at like HCl, it would be chlorine is 3.5 minus hydrogen is 2.1, so 1.4. I'd be right around here. So HCl is very polar covalent. This side negative, this side positive. Okay. Compare that to like HF. I got 4.1 minus 4.0 minus 2.1. So I got almost 1.9. And I'm still extremely polarized, but that's still covalent bond. Okay, This is where you get hydrogen bonding. The electrons are being pulled away. In HCl, there's still electrons around the hydrogen, around the nucleus. What you get is the nucleus being exposed as the molecule becomes more polarized. And if I was to put this in water, and the one thing I'll say about this chart is it's not always linear like this. If I had something like C double bond O, well, I have an equal pole left as an equal pole right, and it's kind of like vectored forces. Individually, this bond is highly polar if I looked at something like carbon monoxide. But when I look at carbon dioxide, it doesn't really become a dipole because the two forces cancel each other out. So, in fact, carbon dioxide is not polar at all. So you have to actually not look at just the difference, you have to look at the structure of the molecule. Carbon dioxide is very polar covalent because there's no cancellation of that bond. Okay. With water involved, we always have the problem then. The H, because of the size, oxygen's very small, chlorine's very large. The H would actually be more attracted to the O in water, and it becomes H3O in acid. And that's why HCl and HBr and HI, they're all strong acids because the H has more attraction to that oxygen. Now this is kind of an oddity. You would expect HF, because it's so highly polarized, to actually become acidic, but the problem is that the H is more attracted to the F because of the small size of the F compared to the O. So it's got more of a coulombic force connected to the F than it does with the H. And that means HF stays together as a weak acid. And I guess if I was to put fluoride in water, and then you actually look at the H of the water, the acidity of that H, it would actually go to the F to become HF and leave you with OH. And that's why fluoride is a base in water. It actually takes the H away from the water to act as a Bronsted-Lowry base. And the water would become the acid in this case, forming hydroxide. Okay. All right. So if I go back to my sheet, I wanted to get that sheet in there somewhere. I think the last, I only stuck these in here because they're all organic. If I have a pure hydrocarbon, it's LDF. That would be the weakest force. If I was comparing hydrocarbon to hydrocarbon, the heaviest one has the most electrons, is always the most polar, the strongest force. The lightest one always has the least electrons, the least polarizable. And then if I stuck a halogen on there, that would create a dipole. This would be an ether, which would give you a little bit of a dipole. An acetate would give you a little bit of a dipole. And then you have, I put a carboxylic acid and an alcohol. And these both would be hydrogen bonding. Okay. And I suppose with the double bond out here, you get more hydrogen bonding, having the extra oxygen. But I was just comparing the forces on those. And that's it. I got one other sheet that I posted up. And this is, again, this kind of focuses on phase diagrams and gas, liquid, solid. Going backwards like this, that would be water. I know that's water because that always shows you that the water is one of the few molecules where the liquid is more dense than a solid. I think, you know what, My experience, if I was making bismuth crystals, the bismuth crystals, the solid floats in the liquid. So I got a feeling that bismuth is also has a solid that's less dense than the liquid. If I check that out, I don't know. That's just by what I was watching the crystals float when I was making it. Supercritical, that's where you're past your critical temperature, and these are some of the technologies you can get from supercritical. Drying, that's where you get like freeze-dried coffee. Uh, you can get dispersions, paints, adhesion, extracting. This is how you extract caffeine from coffee. Dyes. In painting, in the old days, you would paint with liquid. You'd spray on a liquid, spray paint a car. Nowadays, you hear like the aluminum is powder coated aluminum. In a supercritical phase, you can actually take the powder and have it deposit right onto the metal, and that creates a better bond. And another thing they do is they'll give the powder the charge. They'll make the car have a charge like a negative, and the powder will be positive, and then you get a bonding between the positive and negative particles. And so today, painting is much different than in the old days. They used to paint with particles, and you'd have a lot of overspray. Today, when they paint a car, all the spray goes right on the car because it attracts right to it. There's a definition of critical pressure, critical temperature, and both together make the critical point. Okay, and if you add dry cleaning, they used to use carbon tetrachloride, uh, which became a hazardous waste product. So all your dry cleaners were putting out carbon tetrachloride, and in the 1980s, in the late 70s, they were digging up those places, and they were becoming Superfund sites that they had to clean up. Today, dry cleaning technologies really changed. When they go to dry clean your clothes, the biggest thing is they're taking oils and greases out of your clothes that come from your body. So you're not washing them with water and soap. And the new technology is to take carbon dioxide. Okay, you put carbon dioxide in its supercritical phase where it's more like a liquid, and literally you're running carbon dioxide through your clothes, and the carbon dioxide as a solvent is washing out all the greases and oils. And then if you lower the pressure, the carbon dioxide will turn back into a gas, and once it's out of the clothes and it's done its job, it leaves behind all the grease and oil, and you can re-pressurize it and recycle the carbon dioxide and reuse it. So dry cleaning machines today can cost a couple $100,000, but their technology is they're really green in that they're not putting out any hazardous waste, and the carbon dioxide is being recycled, and that's pretty interesting. And like I say, for extraction for things like caffeine, supercritical fluids are interesting. All right, that does it for the chapter, and good luck.